Welcome everyone. In this lesson, we're just going to look at a few more properties for the definite integral that are sometimes going to help us calculate some more complicated integrals that we might be interested in. And these three properties that we're going to look at, they all have to do with the limits of integration. So if you kind of look at these three properties that we have, our function that we're integrating in each of these, that's not the main story. It's just f of x. The main story in each of these three properties is the limits of integration. So something's happening or something is special about the limits of integration in each of these. So let's just go back to the other properties that we looked at in class. Where were they? Here we go. These were the other properties that we looked at. Now for these were the limits of integration weren't the main story in these. They were just a and b, and it just stayed a and b. So the limits of integration weren't the interesting thing for these properties that we looked at in class. The interesting part was, well, what's going on with our function? Or, maybe we have a constant times a function. What can we do with that? So the interesting thing for these three properties was the actual function we were integrating. So the next set of properties, though, these all have to do with our limits of integration. All right, so let's look at the first one. What does this first property say? Well, it says if we have a definite integral, so we're just integrating some function f of x from a to b, what we can do is we can actually switch the limits of integration. And what happens is that makes the result negative. So if we switch the limits of integration, we can do it. We just got to make sure we make the result negative. So we just got to negate it. Okay, so that's the first property there. We can switch our limits of integration. So if we start where we're integrating from a to b, well, we can swap it around. And instead, we can integrate from b to a. And the only thing special, or the only thing we have to do then is just make the whole thing negative. All right, so what about that second property? Well, on the second one here, what does this say? If we're integrating, if we have this definite integral, so we're integrating some function f of x from a to a, well, we end up with 0. So for this one, the limits of integration are actually the same. So if our upper limit and our lower limit are the exact same thing, well, then the integral is going to be 0. And we get 0 for our integral. And let's for this one, we're going to come back to this. So once we look at kind of our main way of interpreting the definite integral, we're going to see that definite integrals, they're related to area. And so we're going to come back to this property and maybe all three of these properties. But primarily these two. And it's going to kind of make more sense once we start interpreting the definite integral in terms of area. All right, this last one here. Let's look at this last one. So what this says is we can either combine, so you can read this a few ways. So let's just look at it. If we're doing a definite integral of some function f of x, and we're integrating from a to m, and then we have another integral from m to b of that same function, well, we can just combine them into one integral and just integrate all the way from a to b. So the thing that we have to be careful of here is that this function, we have to be integrating the same function for this property to work. So we need the same function here. And when we do this, if we're integrating from a and then we integrate from m, what has to also happen is this kind of middle limit of integration here that kind of happens in between a and b. Well, it has to be the same number. And let's think of this graphically. And when we do this, we want to think of our limits of integration as kind of a section of the x-axis. So let's start with the interval from a to b. So let's look at this section of the x-axis where we're going from a to b. And for this discussion, let's suppose that m is just some number in the middle. It doesn't necessarily have to be in the middle. This property works if it doesn't, but conceptually it makes the most sense if we pick m to be somewhere in the middle. So let's maybe pick it here. All right. So what does this property say? Well, this first integral, the integral from a to m, what we're doing is we're just integrating our function over this section of the x-axis. And then the next integral here, where we're integrating from m to b, well, that one we're integrating over that section of the x-axis. We're going from m to b. And what this property says is that rather than doing one section here and then another section here, if you kind of stop and start at the same place, well, you can just kind of eliminate that middle point and just integrate all the way through. So rather than going from a to m and then from m to b, instead of breaking it apart like that, we can just go all the way from a to b, and we get the same result. So again, this property, we'll come back to it when we start talking about area, because there's a way to think of this as just kind of we're adding areas together. But let's try a little example where we use this property. So let's suppose that we want to calculate the integral of some function f of x from 0 to 5. Now, we don't know what f of x is, but we do know that the integral of this function from 0 to 6 is equal to 8, and we know that the integral from 5 to 6 is equal to 7. So let's kind of think of a number line here. Let's kind of graph out the section of the x-axis. And so what we see is that we're interested in the interval from 0 to 5. We're also interested in the interval from 0 to 6. And then we're also, the last one here is from 5 to 6. So kind of the largest interval here is going from 0 all the way to 6. And then we have 5 somewhere kind of in the middle there. Okay. So let's think about what we know. So we know that the entire, if we integrate all the way from 0 all the way to 6, so we know that integral is equal to 8. So if we integrate all the way from 0 to 6, our integral is 8. We also know that the integral from 5 to 6, if we just do this little section here, if we integrate our function from 5 to 6, that integral is 7. And what we're trying to figure out is the unknown part is this integral from 0 to 5. So this is really the unknown quantity. The integral from 5 to 6 we know is 7, so that's our integral value there. And then if we do the whole thing going all the way from 0 to 6, we should end up with 8 as our value. So what this property tells us, this nice kind of integral property, is that if we integrate from 0 to 5, and then we integrate from 5 to 6. So if we integrate from 0 to 5 we stop, and then we keep going. We integrate from 5 to 6. Well, what we should end up with then is just the entire integral going all the way without stopping in the middle. So we should end up with the integral from 0 to 6 of our function. And then we can just fill in what we know. So we know that the integral from 5 to 6 is 7. We know the entire thing should be 8. And the one that we don't know, we're just going to leave it as the integral. So the integral of 0 to 5 f of x dx. So what we get is this an equation here. And the thing that we don't know is this value of the integral. So, don't be thrown, even though this equation looks really complicated, we're just going to solve for this unknown quantity. So think of this as just a really big, fancy x that we need to solve for. And what would we do? Well, we're just going to subtract 7 from both sides. And we get 1. So that integral from 0 to 5 of that function must be equal to 1. And that makes sense. If we go from 0 to 5, well, whatever we get going from 0 to 5, if we add it to 7, has to equal 8. And the only number that does that is if this was 1. Okay, so just a little fun there with that property. Let's try probably a more common example where we would use this property. So this one helps us integrate piecewise functions, and that's what we have here. This is a piecewise function. We've looked at these before. All right, so what is our piecewise function? F of x is equal to x squared if x is less than 1, and then if x is greater than or equal to 1, we end up with 2 minus x as the output. So this is a piecewise function, and there's kind of two pieces. And the one thing that we note is that our function here is continuous at x equals 1. So when the pieces of our piecewise function come together, they come together nicely. So there's not a jump in our graph. So you can check this out by doing the limit of kind of the left-hand piece, the limit of the right-hand piece, and you see that they kind of come together. All right, so this is a piecewise function, and we just note that it's continuous. So what we're able to do then is we're interested in calculating the integral of our function f of x from 0 to 2. And so we're going from 0 all the way up to 2 here. And if we look at our piecewise function, the pieces kind of split apart right in the middle, going from 0 to 2. Our pieces of our piecewise function split apart at x equals 1. So there's kind of two different formulas that we would need to use here. So our strategy, if we're going to calculate this integral from 0 to 2, well, rather than trying to do this outright, we're going to split up this integral based on the pieces of our function. So we're going to integrate from 0 to 1, our function, and then we'll integrate from 1 to 2. And why did I choose 1? Why did I choose to split up our interval here at 1? Well, that's because our piecewise function splits up at 1. All right. So let's rewrite this first integral. Now, once we split up the limits of integration like this, we can put in the actual formula for our function on each of these pieces. So if we're looking at the interval from 0 to 1, this is the first piece. So we can rewrite that first integral as the integral from 0 to 1 of x squared. And so the way I know that is these limits of integration, we're going from 0 to 1. So we're using all x values, or mostly x values, except the one endpoint, when x is less than 1. So that's why I end up using the x squared piece here. Now for this other integral, we're going from 1 to 2, so we're using primarily x values that are greater than 1. So that tells me for this other integral, I'm going to use this 2 minus x piece. And we're going to integrate from 1 to 2. And just because our function is continuous at x equals 1, we don't run into any issues by splitting it up at x equals 1. So using these different formulas here is okay. All right, so we have our definite integrals all split up. Now we just want to calculate them. So let's do the first one here. Let's get the antiderivative of x squared. So we do our power rule, 1/3 x cubed. Then we're going to evaluate that from x equals 0 to x equals 1. And to that, we're going to add our second integral over here. So let's get the antiderivative. So the antiderivative of this function is going to be 2x minus 1/2 x squared. So the antiderivative of 2 is 2x. And then the antiderivative of that negative x is negative 1/2 x squared, a little bit of power rule. And we're going to evaluate this piece from x equals 1 to x equals 2. And then we just plug in. So for the first one, let's plug in. We end up with 1/3 times 1 cubed minus 1/3 times 0 cubed. And then let's plug in what we get once we get to the do this evaluation here. And we plug the top number in first. So the x equals 2 goes in first. We're going to end up with 4 minus 2. And then we subtract, and then we plug the 1 in. And we get 2 minus 1/2. And, I mean, we could clean this up if we really need to. The first part here ends up being 1/3. And then we get a 2 minus a 2. And then plus 1/2. So this actually ends up being, if we clean all this up, 1/3 plus 1/2. But again, when we're doing these definite integrals, especially for like exams and things, I'm not going to expect you to simplify this down. So if you want to leave it like that, perfectly fine. Maybe some of the easy things you can do. So 1 cubed, it's just 1. 0 cubed, well, that's just going to make that whole thing 0. So simplify the easy things, and then that should be good enough. In any case, this is what we get. All right, so that'll do it. Just a little bit, a few more examples of these properties for definite integrals and where we might use them. So in class, we're going to see, well, we're going to start looking at some interpretations for what this definite integral is calculating. And we're going to look at it in the context right now of motion in a straight line. So we'll see you then. Bye-bye.